Okay, so moving on. Now we're talking about salts as cations and anions. So classify each anion as a weak base or pH neutral. Okay, so when I think about these, so a strong acid. So strong acid, hydrochloric, hydrobromic, hydriodic, nitric, perchloric, hydrogen sulfate, sulfuric acid. The first acid only. So that means that chloride, bromide, iodide, nitrate, and perchlorate, these will not react with water. All others will. And HSO4 minus, this is actually a weak acid, so keep that in mind. So the anions of the strong acid, with the exception of bisulfate from H2SO4. So remember that these are the conjugate bases of the strong acids. These are all neutral with respect to water, but not HSO4 minus. So classify these as a weak base or pH neutral. So for this one here, for A, this is from HNO3, which is a strong acid. Therefore, this is neutral. This does not react with water. So for B, this is from HNO2, which is a weak acid, which means this is a weak base. So, and this one here, this is acetate. This would be C2H3O2H. And this is acetic acid. This is a weak acid, so this is actually a weak base. Again, the logic for this is the anions, the conjugate bases of HCl, HBr, HI, HNO3, and HClO4, these are all neutral with respect to water, with the exception of HSO4, because that's a weak acid. So that's a weak acid. So everything else, the only ones that are neutral are these here that are circled. Everything else is going to, at least for an acid, is going to be a weak base, with the exception of bisulfate, because that's a weak acid. Okay, so let's move on and talk about pH of the salt solution. So let's see here. Sodium formate, pH of a 0.1 molar sodium formate solution. And, well, what's the Kb for this? Well, you can look up the Ka for formic acid. Ka for formic acid is 1.8 times 10 to the minus 4. So what's the Kb? You actually have to calculate it out by using the fact that Ka times Kb is the Kw. So, but then it's just the same. So 0.1 molar of this, so it's going to be 0.1, 0, 0, shift right, so minus x plus x plus x. So 0.1 minus x, x, and x. And our Kb is going to be HCHO2 hydroxide. And again, writing the hydrolysis, this is considered chemistry common sense. So you have to know how to be able to write this expression. And this is going to be equal to x squared over 0.1 minus x. Apply the x's small approximation, x squared over 0.1. X equals the square root of 5.6 times 10 to the minus 12. So that's going to be 2 to 3 point something times 10 to the minus 6. And so this is equal to 2.4 times 10 to the minus 6. And then then we plug this back in here, and then the pH is 14 minus the POH equals 14 minus a minus, oh, too close, minus a minus log of 2.4 times 10 to the minus 6 equals 8.38. And there's the answer. Okay, so recap for this one. So you, the student, you have to know the hydrolysis expression. So you have to know that what happens when an anion like the formate anion reacts with water. And you also have to know that the Ka times the Kb equals the Kw. And so you're not going to find, you might be able to find this if you do a Google search on the Kb of sodium formate. But if you try and look in your textbook, you're not going to be able to find it because this is probably a fairly common problem. Let's say you're looking for the Kb for something else that's a little more complicated, or a little less common, I should say, then the Google search might not get that for you. So you have to know how to do this if you're working on a more advanced problem. Some weird organic molecule, for instance. Okay, but then you have to write the hydrolysis expression and construct your ice chart, then write the equilibrium expression, and then solve, and then calculate the pH from the corresponding hydroxide anion. And voila, 8.38. So, okay, going back to talking about salts, so if you have a strong acid and a strong base, this forms a neutral salt. Of course, with the exception of sulfuric acid, because the bisulfate anion is a weak acid. So remember, that's the exception. But a strong acid, with the exception of sulfuric, plus a strong base, this will form a neutral salt. And the strong bases are the alkali and alkaline earth metals, hydroxides. And then a weak acid plus a strong base makes a basic salt. A strong acid plus a weak base forms an acidic salt. And if there's a weak acid, weak base, it depends on the relative size of Ka and Kb. You cannot determine that just off the fly. You have to look and see which one is which. So, but the reason why, the reason why is the acid bases, the conjugates do not react with, the strong acid bases do not react with water, but weak ones do. So I always kind of remember like a weak acid and a strong base. The strong base is so strong it makes a basic salt. But I mean, that's a stupid way to remember it, but that's also how I remember it though. Okay, so determine whether each is what the solution is acidic or basic. So A, strontium chloride. So we have strontium hydroxide and hydrochloric acid. So strong acid, strong base. This is going to be a neutral salt. So you have a strong acid, strong base. B, aluminum tribromide. You have aluminum hydroxide, which would be a weak base, and then hydrobromic acid. So you have a strong acid and a weak base. This is going to be an acid salt. Okay, and then you have methylamine nitrate. CH3, NH3, NO3. So this part here, this is from a weak base, and then this here is from a strong acid. That means that this is an acid salt. So you have a weak base and a strong acid. And likewise, this one here, you have sodium formate. We already did this problem. You have a strong base and a weak acid. This is then a basic salt. And now, for ammonium fluoride, this one you can't tell off the top because you have a weak base and a weak acid. So you have to look at the different strengths of these, and it turns out that your Ka, so for fluorine, it is let's see here. You have to look at ammonia. So the Ka for hydrofluoric acid is 6.8 times 10 to the minus 4, and ammonia, the Kb is 1.76 times 10 to the minus 5. So minus 5 minus 4, the weaker acid is stronger than the weak base, therefore this is an acid salt. So it just depends on relative strength. In this case, since the Ka value is larger than the Kb value, that's how you can tell. But basically, it just depends on that one. But that's a harder one there. You have to look that up. So let's see if you're following this. Potassium acetate. This is going to be basic because you have potassium hydroxide, strong base, and acetic acid, weak acid. So strong base, weak acid. That means basic or alkaline salt. All right, the next thing I talk about are polyprotic acids. So you can see here so polyprotic means many, so two or more protons. And you can see, so sulfuric acid, I mentioned, the first proton is strong, the second one is 0.12, or 0.012. It's a pretty strong weak base still. In various other ones, oxalic acid, sulfuric acid, phosphoric, citric, ascorbic. So that's anti-scurvy acid, ascorbic acid, and carbonic acid, and there's triprotic, there's tetraprotic acids even. So you can have many different types of protons on your acids. So, but each of these, you notice that each of the equilibrium constants, they get smaller and smaller as going on. Let me show you how to work then for sulfuric acid. This one's always really challenging. So truth of the matter is you can discount the other protons for polyprotic usually because they're very small, with the exception of sulfuric. So sulfuric can be a fairly difficult one. So what is the pH of 0.01 molar sulfuric acid? So the Ka1 is strong, the Ka2 is weak. And I've gone ahead and written the ice chart. So the first one here, we have sulfuric acid, straight arrow, breaks apart. It's a strong acid. There is no equilibrium. So our initial change equilibrium, there is no H2SO4. It all breaks away. It all turns into hydrogen ion and bisulfate. And then now you have the second equilibrium here, and you initially have 0.01 molar bisulfate anion, and you already had 0.01 molar from here, from the common ion. And then you have another shift. You shift right, and then you have the equilibrium expression. So our Ka2 is the equilibrium expression there, equals 0.012, equals that. And guess what? You cannot apply the x is small approximation. So you have to FOIL this. So you have to go ahead and FOIL this. So let me go ahead and do that for you. So that means keep on going, 0.012 times the quantity 0.01 minus x equals, I'll go ahead and write this x, okay, 0.01x plus x squared, and so this is going to be 0.00012 minus 0.012x equals 0.01x plus x squared. So then you have to add that to both sides. So you have 0 equals negative 0. Actually, let's go ahead and write it out. We have x squared, and it'll be plus 0.022x minus 0.00012 equal, that's already equals 0. So let me go ahead and make sure I set this up correctly. Yes, I have set that up correctly. And now you have to take this and you have to put this into the quadratic equation, right? So you have the ax squared plus bx plus c equals 0. So that means that our x is negative b minus 0.022 plus or minus the square root of b squared, 0.022 squared minus 4 times a is 1 times c minus 0.00012 all over 2a, which is 1. And solving for x is equal to minus 0.027 or 0.0045. This one is not correct because it's a negative value. So that's the one that's correct. So that is our x. And we can then apply that back into here, where our hydrogen ion concentration is 0.01 plus 0.0045, which is 0.0145 molar. And then the pH is the minus log of the hydrogen ion concentration, which is minus log 0.0145, and that equals 1.84, like so. Okay, so this is a hard problem if you hadn't noticed. Oh, I always gets my brain going to do this. All right, so how do you do the pH of a dilute sulfuric acid solution? So it is a common ion problem. So remember, sulfuric acid is a strong acid and a weak acid all put together. And again, this is not my fault. This is the way the world works. I'm not making this up. This is something that we observe, and this is how it works in the world. And so sulfuric acid is a strong acid, at least the first hydrogen is. So it's a one-way street. It completely breaks apart, 100% ionizes into hydrogen ion and bisulfate. But then bisulfate is a weak acid, so it has an equilibrium. It has a common ion with the strong acid solution that was there before it. And then we have the equilibrium expression is 0.01 minus the extent of reaction plus 0.01 plus the extent of reaction, and sulfate being the extent of reaction. So we write our equilibrium expression, products over reactants, that is 0.012, and we put in our x extent of reaction unknown into that, and then we have to FOIL it and set it up in terms of the quadratic equation and solve for x. If you have a sweet calculator and you're doing this in a computer, go ahead and solve it. You don't have to go through all this. You can just do it in one direction if you want. But you cannot use the x small approximation for this one. But you still have to either have the program or you, the user, have to pick the right answer because there's two answers. Again, this is from the fundamental theorem of algebra. Not that there's anything special about this. It's just on one answer, there's only one real answer for this. Otherwise, I mean, there would be a fallacy. You would probably have a what is that called when you have something that'll stop the paradox. You would have a paradox. There is no paradox in this. There is no end of the universe in this. It's just math is bad and the real world is not. Okay, so then you pick the proper term for the solution, and you apply it, and you get a hydrogen ion concentration of 0.0145 molar, which corresponds to a pH of 1.84. Okay, so that's a long problem. Whew. All right, now let's start talking about conceptual stuff. So why do acids act like acids? If you ever wondered that. And generally speaking, the weaker the bond to the hydrogen, the stronger the acid. So if you look here for, you have a bunch of acids here. In the bottom, you have, so let's see here, there's perchloric, then chlorous, and then there's hypochlorous. So in the bottom, it's hypochlorous acid. It has the fewest oxygen. That has the lowest value of Ka. Then chlorous acid has got slightly higher. Chloric acid is even greater than perchloric. Of course, you keep on adding oxygens. It's a strong acid. Why is that? Because these oxygens, they act like electron sinks. So these oxygens, they are pulling electron density away, and it makes this bond very weak. This weak bond, should I say weak? That weak bond is easy to break. If it's easy to break, then it's easy to ionize, which makes it a strong acid. So the weaker that hydrogen bond, that oxygen hydrogen bond, the weaker the acid, or just the weaker the bond, the hydrogen in general, that's the weaker or the stronger the acid. So that's where it comes from. And then when you start studying organic chemistry, for instance, this hydroxide. So hydroxide is considered an acidic hydrogen, but water is more acidic than that. But you can take, so this is methanol. If you take something like sodium metal or potassium metal, and you throw it into methanol, it'll rip off that hydrogen, and you'll form the methoxy ion. And the methoxy ion is a very, very strong base, a stronger base than hydroxide. So if you need to use a very, very strong base, you can use an alkali metal and an organic alcohol to make even stronger. Of course, you can learn more of that next time. So with this in mind, which of these protons is more acidic? So you have methanol, and then you have formic acid. So the thing is, the formic acid here on the left, those oxygen groups, these are drawing electron density away from that bond. So the electron cloud just migrates away from the hydrogen, and because of that, that makes that hydrogen very, very easy to break off. And that group is also called a carboxylic acid group. So which one is more acidic? It is A, is the carboxylic acid, versus B, the alcohol. And let me say something more. If you want this to be even stronger, if you put like a fluorine here, then you would even have more electron density being drawn away to that. Or if you didn't have a fluorine, you even another halogen like a chlorine, that'll even rip more electron density and make that even a stronger bond. So you can make even stronger acids that way. Okay, so and then what about Lewis acids and bases? We talked about acids and bases in terms of that. So we can also have Lewis acids and bases. So aluminum trichloride is an acid and ammonia is a base, and it can form this molecule here. And the way that Lewis acid, so every single acid is actually a Lewis acid because it works by transfer of electrons. So the electrons, so from water, the electron pair will transfer to the antibonding orbital of the hydrogen chloride molecule, and the hydrogen will pop off, and then it'll just be soaked up by the water again. But so that is one thing with Lewis acid and base. So the acid being an electron donor, base being an electron base being electron donor, acid being an electron acceptor. It works, and it works by the molecular orbital theory. You have to apply molecular orbital theory for it to make sense. And likewise, here are some Lewis acids and base reactions that way. So we tend to think of things, at least in this course, more the Bronsted-Lowry, the proton donor, proton acceptor. But the Lewis base acid, the acid base theory works as well. And some reactions that you think they're acid-base reactions, but they're not going to be in a water solution. So when you're dealing outside of a water solution, that's one thing you have to apply the Lewis acid-base theory to that. So next chapter we'll talk about other types of equilibria, not just, acid and bases, we'll apply buffers, and we'll talk about other types of equilibrium. So we're done there for this chapter, and next one is also interesting.